constant in his equations to account for the fact that the universe was stable. Now, this was before Hubble did his observations, found more galaxies, and eventually we saw that the universe is not only stable as in it's not collapsing, but it's actually expanding. And then later in the 20th century, we even found that its expansion is not only happening, but it's accelerating. So that's where dark energy comes in. This phenomena of the expansion and this anti-gravity, this history of the physics evolving is dark energy. Thank you, Alex. I'm looking at the comments over there too on my laptop. So this cosmological phenomena, that's dark energy. Some people consider it they consider it almost like a, like you'll hear people talk about it as cosmological constant. They think of it as literally like maybe it's a property of the universe. It's almost like this, like it's almost like the universe does that. Like maybe that's what it is. You know what I mean? Like it's almost like an intrinsic property almost. Now I'm not saying you have to be convinced by it, because it is still the case that dark energy is a mysterious topic, so we should try to understand it more. But dark energy is almost like this property. Dark matter, on the other hand, is somewhat different. It's they could be related. But dark matter seems to be more of like this, like weird invisible matter, like stuff that's there but we can't see it because it doesn't interact with light. And it very well could be a type of particle that we haven't discovered yet. So there are dark matter candidates, and there are dark matter candidates, and we spoke about how neutrinos, WIMPs, and machos, those things are acronyms, were dark matter candidates. So we talked about neutrinos being a dark matter candidate because neutrinos also don't interact with photons. Or sorry, neutrinos also don't interact with electromagnetic force. So, so we know of other particles that are also elusive. They're also real and they're also elusive. So, maybe dark matter is a type of particle that we just haven't discovered yet, because we are not necessarily sure that we have discovered everything there is to discover, even in a field like particle physics. In fact, we haven't, because there is this topic of dark matter that is also a mystery. So we talked about it, but basically we considered neutrinos could be the explanation for the invisible matter, because there is a lot of neutrinos being formed in pretty much every process as well. We did some math and we found that no, actually neutrinos don't really account for it enough. And then we considered weakly interacting massive particle with basically the inspiration that, well, neutrinos didn't do the job, but maybe we can dream up a different type of particle that has more mass that could kind of act like a neutrino, but maybe that's what dark matter is. So that's a WIMP. And then we talked about machos, which were basically massive compact halo objects. So dim objects in the halo of our galaxy, where they don't really contribute much to the luminosity, which is exactly, the issue with dark matter. Dark matter is dark. It's not bright. We didn't know it was there, but apparently it's there, type of thing, So we considered these types of candidates, and so far we haven't really determined exactly what it is, and the search is still on for dark matter. But dark matter seems to be, it's not, I know it's confusing to say the sentence like this, but dark matter seems to be something substantial, something matter, like some stuff. It seems to be some stuff, whereas dark energy is more like this, almost like this property of the universe, if that makes any sense. So I just wanted to give you that view, which hopefully kind of helps to, put things in alignment. But at the same time, let me just wrap this section